Good day, everyone. Welcome back to General Mathematics. It is still me, Engineer Omengan, to teach you exponential functions. Welcome to Exponential Function, LBV GMAT 1-4.6b to 1-4.7. In this topic, our most essential learning competency determines the intercepts, zeros, and asymptotes of an exponential function and solves problems involving exponential functions, equations, and inequalities. In this video, the topics covered are zeros of exponential functions, asymptote of exponential functions, and real-life problems involving exponential function. For our learning objectives, by the end of this video, we want to know or determine the zeros and asymptote of exponential functions and solve real-life problems involving exponential functions. Now for the zeros of exponential function, to solve for the zeros of exponential functions, simply solve for the equation f of x be equal to 0. So in other words, the zeros of exponential function is also the x-intercept of the function. But instead of getting it in the point form, we will just get the x value. Let's look at this example. We have here f of x equals 3 raised to x minus 9. So the zeros of exponential function is also the x-intercept of the function, but we do not express it in point form. So to solve for the x-intercept, we let f of x or y be equal to 0. And then we solve for x. So we have 0 equals 3 raised to x minus 9. And then by addition property of equality, we have here 9 equals 3 raised to x. So by the property of equality, we must express both sides of the equation with the same base. And we know that 9 is 3 squared. So we have here 3 squared equals 3 raised to x. And by extension, we have here x is equal to 2. And this will be our zeros of exponential function. Now let's graph our example. So we have f of x or y equals 3 raised to x minus 9. So looking at this example, we know that the zeros are similar to our x-intercept. So we will just look for the portion or the point at which the graph passes through the x-axis. And by inspection, this is at 2, 0. Now, since we are talking about the zeros, we will just take the x value, which is positive 2. For problem number 25, determine the zeros of the exponential function f of x equals 2 raised to 4x minus 2 minus 16. The zeros of exponential function is similar to the x-intercept, but we do not express it in point form. But instead, we will just get the x value. So for the x-intercept, we let f of x be equal to 0 and then we solve for x. So we have here 0 equals 2 raised to 4x minus 2 minus 16. And by addition property of equality, we will transpose negative 16 to the other side, making it positive 16, giving us 16 equals 2 raised to 4x minus 2. Now, before we perform the property of equality, we must express both sides of the equation with the same base. So we know that 16 is 2 raised to 4, giving us 2 raised to 4 equals 2 raised to 4x minus 2. And by extension, we will know that 4x minus 2 is equal to 4. By property of equality, we will add positive 2 to both sides, giving us negative 2 plus positive 2 is 0. So we will have 4x equals positive 6. So we divide both sides by 4, giving us x equals 3/2. Problem number 26. Determine the zeros of the exponential function f of x equals 3 raised to x plus 1 minus 27. So again, the zeros of exponential function is similar to the x-intercept, but we do not express it in point form, but instead, we will just get the x value. So, for the x-intercept, we let f of x be equal to 0, and then solve for x. So we have here 0 equals 3 raised to x plus 1 minus 27. Now, by addition property of equality, adding 27 to both sides, it will give us 27 equals 3 raised to x plus 1. So before we perform the property of equality, we must express both sides of the equation with the same base, and we know that 27 is also equal to 3 cubed. Now, it will give us 3 cubed equals 3 raised to x plus 1. So by property of equality, it will give us 3 is equal to x plus 1. And we subtract 1 to both sides, giving us 2 is equal to x, or x is equal to positive 2. Next problem, problem number 27. Determine the zeros of the exponential function f of x equals 2 raised to x minus 2 minus 16. So again, the zeros of exponential function is similar to the x-intercept, but we will just get the x value. So, for x-intercept, we let f of x be equal to 0 and then solve for the value of x. So we have 0 equals 2 raised to x minus 2 minus 16, and by addition property of equality, we add 16 to both sides, giving us 16 equals 2 raised to x minus 2. So before we perform the property of equality, we must first express both sides of the equation with the same base. We know that 16 is also 2 raised to 4, giving us 2 raised to 4 equals 2 raised to x minus 2, and by extension or by property of equality, we have 4 is equal to x minus 2. We add positive 2 to both sides, giving us x equals 6. Now let's go to the asymptote of exponential functions. An asymptote is a line that a curve approaches as it heads towards infinity. Now, let's take note of the term approaches. The curve approaches the line. So it means that the curve will only approach this line, but it will never touch this. Alright? Then the asymptote is just a virtual line. So it is not really a part of the graph of the function. So take note that the exponential functions only have horizontal asymptote. Now let's take a look at this example. We have here f of x equals 3 raised to x minus 9. And the asymptote is similar to our range. The asymptote of the function is defined by the term after the number that contains the exponent. So from this example, f of x equals 3 raised to x minus 9, that is negative 9. That is the term after the number that contains the exponent. Therefore, the asymptote is y equals negative 9. Now let's graph the function. We have here y equals 3 raised to x minus 9. And let's see if the line y equals negative 9 is really its asymptote. So again, when we say asymptote, the curve will only approach this line but basically not touch it. So when we zoom in, this line will just approach this curve but will never touch it. So as it approaches to infinity, the line will just get closer and closer but will never touch each other. So let's take a zoom again. See, these two lines or these two curves never touch each other. For problem number 28, determine the asymptote of the given function f of x equals 2 raised to x plus 2 minus 5. So the asymptote of the function is again defined by the term after the number that contains the exponent. So if we have here f of x equals 2 raised to x plus 2 minus 5, that is negative 5. So the asymptote is y equals negative 5. For problem number 29, determine the asymptote of the given function f of x equals 3 raised to 2x plus 3. So again, the asymptote of the function is defined by the term after the number that contains the exponent, or in other words, the exponential expression. So from this example, that is positive 3. Therefore, the asymptote is y equals 3. For problem number 30, determine the asymptote of the given function f of x equals 12 raised to x minus 2 plus 3. So again, the asymptote of the function is defined by the term after the number that contains the exponent. So let's remember that even if the function or the given becomes complicated, we will be only concerned with the term after the exponential expression. So from this example, that is positive 3. Therefore, the asymptote is y equals 3. Now let's go to problems involving exponential function. There's no better way to learn this than to solve problems. So, let's solve some problems. For problem number 31, archaeologists are able to estimate the age of organic remains by measuring the amount of radioactive carbon-14 in the organism's remains. If an organism contained 800 milligrams of carbon-14 at its death, the amount A in its remains T years after death is given by the equation A equals 800 times 2 raised to negative 0.000125 T. Find the amount of carbon-14 in the remains 12,000 years after death. Now that we are given the equation for the amount of carbon-14 remains in the body, and that is A of T equals 800 times 2 raised to negative 0.000125 T, where T is time in years. And by inspection, this amount is a function of time. Therefore, if we are being asked of the amount of carbon-14 on the remains at certain time t, we will just substitute the value of t in this equation. So from the problem, it states that the remains after 12,000 years. So we have here A of 12,000 equals 800 times 2 raised to negative 0.000125 times 12,000, giving us 282.84 milligrams. Next problem, problem number 32. Bacteria can multiply at an alarming rate when each bacterium splits into new cells, then doubling. Suppose a certain bacterium doubles every minute, about how many bacteria will there be after 8 minutes? Now we have here the general formula f of t equals a times 1 plus r raised to t. This is our general formula for exponential functions. We will only use this if there is no given function in the problem. So since there is no given function in the problem, we will use this general formula. Again, remember f of t equals a times the quantity 1 plus r raised to t, where a is the initial amount and r is the growth rate or rate of decay in decimal, and t is the number of time intervals. So from the problem, let's see. Initially, there is 1 bacteria. So our initial amount is 1, and the growth rate is stated in the problem. The bacterium splits into new cells, then doubles. So it doubles or increased by 100%. And the number of time intervals, we are asked about how many bacteria will there be after 8 minutes. However, our time interval depends on the amount of time the bacteria doubles. So that is 8 minutes over 1 minute. Therefore, t is equal to 8. So substituting it to our general formula, we have here f of 8 equals 1 times the quantity 1 plus 1 raised to 8. And that gives us f of 8 equals 256. Therefore, after 8 minutes, there will be 256 bacteria. Problem number 33. The population of a certain city has a relative growth rate of 3% per year. The population was 110,000 in 2000. Find the projected population in the year 2005. So again, since there is no given function in the problem, we will use our general formula f of t equals a times 1 plus r raised to t. This is, again, our general formula for exponential functions, where a is the initial amount, and r is the growth rate or rate of decay in decimal, and t is the number of time intervals. So mentioned in the problem, our initial amount is 110,000, and the growth rate is 3% per year. And the number of time intervals, obviously, that is 2005 minus 2000, since we will begin in 2000 and then end in 2005, and our growth rate is per year. So we have here 2005 minus 2000 over 1, and that gives us 5. Substituting it to our formula, we have here f of 5 equals 110,000 times 1 plus 0.03 raised to 5. And that is f of 5 equals 110,000 times 1.03 raised to 5. That is 127,520.1482, or approximately 127,521. Problem number 34. A cell phone worth 12,000 was bought 3 years ago. If it depreciates 5% per annum, how much does it cost now? So since there is no given function or equation in our problem, then we will use our general formula. And that is f of t equals a times 1 plus r raised to t. So again, that is our general formula for exponential functions, where a is the initial amount, and r is the growth rate or rate of decay in decimal, and t is the number of time intervals. So based on our problem, our initial amount is 12,000. And our growth rate or rate of decay is negative 5%, or in decimal, that is negative 0.05. So why is this negative? Because based on our problem, it states that the amount depreciates, or in other words, decreases by 5% per year. Therefore, if the rate is decreasing, we use negative. And for our number of time intervals for 3 years, that is 3 years over 1 year, becomes 3. So, substituting it to our formula, we have here f of 3 equals 12,000 raised to, or times 1 minus 0.05 raised to 3, giving us 12,000 times 0.95 raised to 3, and that is approximately 10,288.5. Problem number 35. A radioactive element has a half-life of 2 weeks. How much of 1,000 gram sample of the elements will remain in 9 weeks? Since there is no given function or formula in our problem, then we will use our general formula. And that is f of t equals a times 1 plus r raised to t, where a is our initial amount and r is the growth rate or rate of decay in decimal, and t is the number of time intervals. So our initial amount based on the problem is 1,000 grams. And our rate of decay is negative 50% or negative 0.5 or negative 1/2. Why is that? Because based on our problem, it is half-life. So the element reduces its amount by half of its original value. Therefore, our rate of decay is negative 50% or negative 0.5 or negative 1/2. And then our number of time intervals is for 9 weeks and it decays every 2 weeks. Therefore, we will divide these two and that is 4.5. Now, substituting it to our formula, we have f of 4.5 equals 1,000 times 1 minus 0.5 raised to 4.5, giving us 1,000 times 0.5 raised to 4.5, and that is 44.19 grams. And that's the end of our lecture. What we learned: we determined the zeros and asymptote of exponential functions and solved real-life problems involving exponential functions. In our next video, we will learn about logarithmic functions. So for more supplementary problems, you may refer to QuexBook General Mathematics Chapter 3.